Welcome back, everyone. This will be session 5 of our series on tornado forecasting. Today we're going to actually look at just weather stuff. No more conceptual models, none of that mess. It's a bunch of maps and good stuff. So we'll hopefully build on what we've done the last few days or sessions. It all kind of blends together to me. And we'll take it from there, and hopefully you'll see this stuff building on itself from the previous 4 sessions. So again, we're going to try to apply what we've already covered so far. All right, again, just to remind everyone what the organization is, we're in session 5. So tonight we will cross the halfway point in this endeavor, and you can see what's coming up ahead. Again, more applied stuff as opposed to building the foundation for a sound forecast approach, which we've been working on the previous 4 sessions. All right, let's review. Recipe for significant tornadoes. We talked about it last week in terms of a theoretical sense, sort of a conceptual model. I mean, what do you need vertical shear and buoyancy? What is this doing? So in this case, we have to have enough vertical shear and buoyancy to get supercell thunderstorms. And the key is we have a long-lived rotating updraft. So that's the important part. Because it's a reproducible convective system, it sets the stage for the other factors that are important in tornado genesis. We need strong low-level shear. Again, last week we tied the low-level shear to low-level stretching. So it's not the rotation in the environment itself, it's indirectly related to the potential for strong low-level stretching as you strengthen the mesocyclone closer to the ground. So that's related to the strength of the low-level shear. And then we talked about LCL height, or in this case, a more general version of that would be rich low-level moisture. We're just talking about what might the thermodynamic characteristics of the roof line downdraft look like. So it's just a matter of putting these ingredients together and what kind of synoptic patterns and mesoscale patterns assemble these ingredients for us. And then finally, we'll talk about this a little bit more next session on, I believe, March 24th, which will be how do we determine whether or not we'll have discrete cells or linear convection, that sort of thing. That's a final ingredient. We'll just look at cases. Obviously, the tornado cases tend to favor discrete storms. Okay, I'm going to look at 4 recent tornado high-risk events. These were all tornado outbreaks, so they were relatively successful forecasts from the SPC perspective. So we'll take a look at these in some detail and kind of look at them in terms of how they assembled the ingredients, and then what were the concerns? You know, how did they vary from event to event, and you know, maybe some things you haven't thought about when you look at these things. Because usually when you get a tornado outbreak, everybody says, oh, of course that was obvious. If you sit there and do this for 25 years straight, there are very few of them that are that obvious, that nothing can go wrong. All right, we're going to start with the mother lode on this one. We can't skip the April 27, 2011 outbreak because that's essentially my career-defining event. That's probably stands a good chance of being the biggest tornado event in most of your lifetimes. I mean, it's going to be difficult to exceed that by a whole lot. So it's helpful to look at that one since that kind of sets the bar. You can see this was a high-risk day, lots of tornadoes. It was in excess of 200 in the initial reports. Quite a few strong and violent tornadoes. Again, the only event that exceeds this one in the period of record is April 3rd and 4th, 74, and that's not by much, just by a little bit. All right, what does this event look like when we break it down into the patterns? So what I'm going to do is for this one, we're going to go back a few days. If you think back to the lapse rate and the moisture sessions, which was back in week 2, we talked about kind of the source regions. You know, where's the air coming from in the low levels in the mid-troposphere? How do we get the lapse rates? How do we generate the moist layer? How do we co-locate these ingredients? Well, obviously, April 27th of 2011 must have been a pretty good example of how you put together the proper ingredients for supercell tornadoes, given it was such a prolific event. And we'll look at how that happened. So we're going to start at 500 millibars here. This is actually 2 days prior to the event. So we've got what already looks like a fairly typical severe weather scenario. And if anyone remembers, there was actually severe weather for 3 days before that. There was actually a high risk the day prior to April 27th. So this was a pretty active sequence. Okay, so we've got a shortwave trough over the southern high plains, West Texas, eastern New Mexico, ridge over the southeastern states. This is a pretty typical pattern. I mean, you know, obviously we want the presence of a shortwave trough because we've talked about their sources for ascent, vertical shear, and differential advection, which all of those help assemble the ingredients for severe storms. And then in this case, it's also helpful to have the ridge over the southeastern United States, because what that tells you, and we'll see that when we look at the moisture return aspect, is that this is a case where there was no recent prior frontal intrusion, a tropical air mass comes back, so we've essentially got undisturbed Caribbean air coming into this system from the south, which is another important aspect. Okay, so looking every 12 hours, and you can see the time date stuff on the bottom there. Fast-moving shortwave trough, Mississippi Valley. There was noticeable severe weather, I think a moderate risk with this event. On the 25th, that wave continues into the Ohio Valley. Notice there's another speed max upstream already digging southeast into the Great Basin. Heights stay high in the southeastern United States. That says that we probably don't get any deep frontal intrusions, and we maintain a long duration return flow. And then we get to the morning of the 27th, and you can track this shortwave trough from the Great Basin to the Red River Valley. Notice it's not particularly high amplitude. It's a fairly strong speed max, but it's not the sharpest trough you'll ever see. Point is, what's downstream from this? So as we look into the 27th, again, you've probably seen troughs that are sharper. You've seen stronger flow. But that does get pretty far south. That's down the I-20 corridor. You've got 80, 90 knot flow, which is fairly strong for the end of April. More importantly, this is co-located with a very warm, moist, and buoyant warm sector, is what it coincides with. So again, this is a case where we're looking several days in advance, and you can see the large-scale pattern is already starting to set the stage on the subsynoptic scale for severe storms. And indeed, that was reflected in the storms the days before. So kind of summarizing that. The so-called lead shortwave trough, you hear people talk about that with some regularity. This is sort of a kind of a prime the pump sort of setup where initially these lead waves induce slow return flow. They start drawing air up from the south ahead of them through differential advection. And as long as you don't remove that air mass, it's sitting there waiting for the next system. So usually it's not the first wave that's the most important one, it's the second or third in the sequence, and that's indeed what happened here. All right, well, let's look at the low-level moisture. This is 850 millibars. Again, we're kind of simplifying this case, but we're going back, again, 2.5 days before the core of the event. There's already southerly flow across the Gulf Coast and the Gulf Basin. Notice the ridge off the southeast Atlantic coast. The gradient supports southerly flow all the way from the Western Caribbean. It's not real strong at this point, but there's already moisture of some consequence inland. You see the low with the first wave. This is moving northeastward toward Missouri, draws air, and then that continues up toward the upper Midwest and the Ohio Valley. But notice down on the Gulf Coast, there's no frontal intrusion. It essentially just brushes by the moist boundary layer and leaves it sitting down there on the Gulf Coast. The morning of the 26th, leads cyclogenesis ahead of the next speed max, draws the moisture back further into Texas, and then we have, and notice it's not a very deep low. I mean, if you just looked at this and thought, oh, wow, one of the worst tornado outbreaks ever, I would expect, a 960 low or something. It's not the case. There's a noticeable low, secondary low towards, say, northwest Arkansas, but notice it's a broad warm sector. The dew points, it's hard to read those, but it's in the teens at 850, which are dew points 55 to 60 Fahrenheit, 4,000 to 5,000 feet off the ground, and a broad fetch of southerly flow, and then you continue to that evening. Again, it's not even a closed low at 850. So this is not a closed, deep cyclone up in the Great Lakes, but look at the gradient flow. 40 to 50, 60 knot flow out of the south or south-southwest over a broad fetch in the southeast, and it also continued up into the mid-Atlantic. So we've been drawing moisture from the south for days in this scenario. So again, I focus on that because it's a long-duration return flow. If you think back to week 2, we looked at the air mass modification and things like the trajectories over the ocean. In this case, it's a fully modified tropical air mass that's returning. So it's Caribbean air. And usually in the early to mid part of spring, that's exactly what you want to see for a big outbreak. Now, as we get into May or particularly June, this becomes kind of quasi-permanent state. As soon as the Gulf Basin gets to the point where it supports a tropical cyclone, you don't really have to worry about moisture. It's just a matter of what are the trajectories. But in this case, we're kind of at the tail end of the classic air mass modification and return flow cycle. But it never hurts to have Caribbean air involved, and that's clearly where this air comes from. And we'll look at that here. So we'll go, again, backing up 60 hours before the core of the outbreak. Surface analysis, again, the light greens and yellows are 68 to 72 dew points at the surface, and I've just sort of loosely sketched in frontal positions and things. And we'll just step through this every 12 hours, and you'll see what I mean by the moisture just sits down here on the Gulf Coast. So this is the morning of the 25th, evening of the 26th, we have a low in the vicinity of the Arclitex. There's already 70 dew points across the whole Gulf Basin. This is 48 hours out, and the flow is out of the south everywhere. So that's definitely a good sign. By the morning of the 26th, the frontal zones look like they may have been suppressed down toward the Gulf Coast. That's largely a reflection of convection the night before. There were a big thunderstorm blow up across Louisiana, Mississippi. That's essentially more of an outflow boundary. Next evening, that's all retreated. We've got upper 60s and low 70s, ubiquitous in the warm sector. Again, you see Lee cyclogenesis again back to the west, over West Texas. The morning, it's consolidated into a closed cyclone close to the Arclitex, and we have the boundary that I've denoted as the warm front in red across Mississippi, Alabama. That's kind of the conglomerate of outflow, and we'll look at that in a little bit more detail toward the end of the examination of this case. But very rich moisture to the south of that boundary, ready to surge northward during the day, and that's actually what happened. So by 0Z, you see the 70 dew points come inland, across Alabama, so the upper 60s and low 70s actually do surge north, so there's actually stronger advection going on during the day of the 27th into the evening of the 28th. And that's in response to the deepening cyclone moving up into the Ohio Valley. But again, it's not an especially deep low, but the gradients were strong, the moisture was prevalent, and we'll see what that looks like when we piece it together in the soundings. Okay, so we've got a broad warm sector. So now we know moisture really is not a concern. And that's one thing I'd like to emphasize is most, if you're gonna, nowadays it's hard not to look at the model forecast. You're gonna see stuff out, 240. I mean, if you're crazy, you're looking at 384 hours. You could even look at the CFS out to 3 and 4 weeks and try to say something about these scenarios. And occasionally there are signals, but the point is these moisture returns are not last second occurrences in most of the serious tornado episodes. It's relatively easy to track the tropical air mass. So it's not so much, it doesn't make it hard when the event occurs, but if you don't look at it that way, it makes it very difficult for you to maintain credibility because you will tend to forecast a whole lot more outbreaks than actually occur. All right. Let's look at the lapse rates. So the same thing, while we've got this long duration return flow, what are the lapse rates doing aloft? So we're going to look at the same kind of thing. This is just the 700 to 500 millibar lapse rate. If you remember, conditionally unstable is somewhere on the order of anything greater than about 6.5 or 7, which would be orange on this plot. And we color fill at, I believe, 7.5. Or 8, so it's 8 degrees C. So that's a fairly steep lapse rate, something that would be representative of an elevated mixed layer. Okay, the morning of the 25th, we have steep lapse rates emanating from northern Mexico, extending across the northwest Gulf Coast. There's another little blob there over the southern high plains. Continue to 0Z on the 26th, you still see a feed of the lapse rates. I don't have the winds plotted, but they're out of the west-southwest down there, so it's bringing air from northern Mexico that extends up into the Arclimus region there toward the Mississippi Delta. Now there's a bit of an interference in the lapse rates by the morning of the 26th, and remember I said there was a big convective blow up. So this is just, there's a lot of moistening, deep convective overturning, and it was reflected in the soundings. However, look back in Texas. Lapse rate plume still sitting there, still goes back into Mexico. The evening of 27th, again, relatively steep lapse rates over a fairly broad area. We continue to the morning. Steep lapse rate plume gets all the way into Georgia. That's not terribly common. So this is one thing you don't necessarily see. And I don't know if anyone's thought about why don't you see the steep lapse rates end up way off to the east very often. I probably mentioned it in week 2. I don't recall exactly. But if you just think about this for a minute, what tends to happen as we have these systems emerge into the Great Plains in the spring? Are they free of precipitation and convection, or are there a lot of thunderstorms? Yeah, MCS is what I heard from somebody. So the point is we get a lot of convective overturning. So it's difficult to maintain these unstable profiles for very long unless you don't get the deep convection back to the west. So this is a typical response in the lapse rate plume. When you don't see widespread convection over the plains, look out downstream the next day. And if you watch that, you'll see it holds true pretty consistently. And again, by the evening of the 28th, some of the lapse rate plume is being cut off, or it looks like it is. You notice that weakness in the lapse rates that runs from the Architects to northwest Mississippi up toward Memphis. That's actually a reflection of the mid-tropospheric front. So that's where you're seeing the strong gradient at 500 millibars. There's cooling temperatures, but you would actually see the mid-tropospheric front there in the classic elevated mixed layers just to the right of that or off to the south. So again, if we just kind of step back, there are lapse rates just kind of hanging around, and that's sitting on top of upper 60 to low 70 dew points. So again, this is the typical scenario with a baroclinic wave. We talked about that in session 1. What's the point of a baroclinic wave synoptically? We have differential advection, so we can get a broad area with steep lapse rates sitting atop rich low-level moisture. Also, it's baroclinic. That means there's still temperature gradients associated with it. So we have vertical shear. You think of the change in the geostrophic wind with height. In this case, in the warm sector, it's usually a veering wind with height. So we've got warm advection. That also says something about the shape and length of the hodograph. If we have deep vertical shear, low-level veering, we get the right hodograph shape. And what this all adds up to is a large window, or window of opportunity in time and space for right-moving supercells. So that's one of the most important things we do when we try to forecast a severe weather outbreak is how big is our window of opportunity in time and space? How many storms? How much opportunity do we have? Because I've emphasized it before, the whole tornado problem is one of probabilities. It's a probabilistic problem. It's not deterministic. You just say, look, you give me more storms for more hours in a favorable environment, and you'll generally see more significant tornadoes. And the only difference between most tornado outbreaks and the mesoscale events is simply the time and space window. And we'll show some smaller scale events that actually have environments that look almost as good as anything you'll see on the 27th. It's just they're confined to a few counties. All right, combining this together, vertical shear and cape, this is just the most unstable cape. Convective inhibition is shaded, and the 0 to, I guess this one's the effective bulk wind difference. So if you just look at this is 2 days out. We have a broad area with at least moderate instability, cape in the 1,500 to 3,000 range, and supercell vertical shear profiles over essentially the entire southern United States. So we continue to the morning or the evening before, 24 hours out, same sort of thing. It goes from Texas and southeast Oklahoma eastward. The morning of the 27th, there's a lot of events that you'll see coming up in the next few weeks that won't have warm sectors at 21Z that look anywhere near as good as this one did at 12Z. Because the Cape, that's on the order of 3,000 into East Texas at 12Z, and a broad area with 50 to 70 knot effective bulk wind differences. And then, of course, by 0Z on the 28th, the outbreak is well underway. You see the classic pattern. There's not much convective inhibition, large shear vectors, large buoyancy, and bad things happen. So again, this is all set in motion by the synoptic pattern. It's just the evolution over multiple days leading up to this. All right, what do the soundings look like that morning? This is Shreveport, 12Z. You see a little teeny shallow stable layer, but large buoyancy, rich boundary layer moisture sitting just above that, and steep lapse rates on top of that. So this is a typical loaded gun sounding where it's just slightly elevated. You look down to Slidell, Louisiana, and again, I was trying to stay away from the convectively contaminated soundings. Slidell has rich moisture beneath steep lapse rates, large cape, also a large hodograph, so there's strong vertical shear, large clockwise turning hodograph. We talked about the importance of that last week. And now you go east, we're going to start getting into some of the things that were concerns about this. You'd say at this point, boy, this looks like an uncontested layup. How can it possibly go wrong? Well, I bet there's a lot of stuff overnight that most of you slept through and didn't pay any attention to, but I had the great privilege of working that midnight shift, so I'll show you some of the complicating factors that did show up. Notice Jackson. We've talked just a little bit about this at this point, but there's a shallow stable layer there and strong low-level warm advection. Keep in mind that little shallow stable layer. So there's something may have happened at Jackson. Now let's see what happened during the day at Jackson. So this is just from 12 to 18Z. Look at the destabilization. So the 12Z soundings in the background. Tremendous low-level warming and moistening, actually slight cooling aloft, but not a lot of change aloft. But we go from not much buoyancy to large buoyancy, and we maintain most of the vertical shear. Now the hodograph isn't quite as large in the afternoon as it was in the morning, but that's still very strong vertical shear, and it's more than compensated for by the large increase in buoyancy. Now continue east. This is the Birmingham sounding, the morning of the violent tornado outbreak. Does that look like the standard loaded gun profile? Any ideas what may have just happened there? Yeah, there was a bunch of convection in the morning. So we had a lot of convection that morning, and I'll show you, and it was an awful lot of convection. So there's an awful lot of questions about what the warm sector is going to look like during the afternoon. But again, Birmingham, 12 to 18Z, huge change. So this tells you, this is the importance of a strong synoptic system. We have very strong horizontal advection. We try to replenish the lapse rates from the west-southwest. We bring more moisture in from the south, and we also warm up as the remnants of the morning convection move by. So we've created, again, another loaded gun. And look at the remarkable change in the hodograph. You've completely inverted the hodograph from morning to, it was a cold advection, counterclockwise curving hodograph with almost no cape in the morning, flipped around to a clockwise curving hodograph with large cape just by 18Z. So that's a remarkable change in the environment just in the 6 hours. Nashville. Remember, this is a strong wave. The low goes up into the Ohio Valley. We have to consider a broad area. This is Nashville, 12Z in the morning, similar to Birmingham. There's a lot of convective overturning that's gone on overnight close to them. But unlike your previous sites that we looked at, there's 18Z Nashville. No change. Convection's still ongoing. So this is a big problem. How far north is the tornado threat going to get? And this is the kind of thing you have to answer if you want to forecast this stuff operationally. And you may not think about it if you're just chasing. You just go, oh, fine, I find a supercell. I don't care what happens everywhere else, but operationally, I have to get the entire event right. And so if you want to do this in a professional sense or just get better as a meteorologist or forecaster, you got to consider the whole area, because occasionally you're going to be stuck dealing with this part one way or another. Okay, so here's 21Z. This is kind of what the atmosphere is recovered to by mid-afternoon. I've sketched in the boundaries. That's the old outflow warm front thing that is moving north in Alabama, Mississippi. You've got the 68 to low 70 dew points. Low to the north. We've got a hint of a surface trough or something, maybe a leftover dry line-like feature that has crossed the Mississippi, which is a little unusual. It's not a real sharp, classic dry line, but there was a sort of a confluence zone that was out ahead of the actual front, and that seemed to be where the storms are initiating. So we put this in terms of Cape, ML Cape. There's a big chunk of 3,000 plus over a lot of Mississippi, Alabama. I know some of the Southeast folks claim, we don't get that kind of Cape. That's just a plains thing. It's like, I don't know how else to explain this. Is that if the environment's there, it works the same way as it does out here. LCL heights. It's moist. We already know we have high dew points, but it wasn't excessively hot in the warm sector. LCLs are generally below 1,000 meters. We've already shown before that that's favorable in terms of the ingredient distribution, so that's well within the range of significant tornadic supercells. Effective bulk shear, very strong. Again, this is strongly suggestive of rotating, deep, long-lived rotating updrafts. Also, we'll talk about it next go-round, the orientation of the shear vectors compared to the boundary orientation. That actually says a lot about what kind of storms you would expect. Would you get a squall line or discrete cells? Effective storm relative helicity, huge values. Consider this, that big corridor of 500 to 600 from the retreating warm front outflow south is co-located with 3,000 Cape. So this is not 500 SRH with piddly buoyancy. This is with 3,000 ML Cape. And when you combine all this, this is the SIGTOR parameter, that's off the charts. That's as good as you ever see anywhere, is that sort of distribution. These values are in the 90th to 99th percentile type stuff. So, and it's over a good part of 2 states. So if you launch multiple thunderstorms into that environment, you almost be assured that bad things will happen. And I think I mentioned last week, in this part of the parameter space, there's about a 60% chance of a SIGTOR every hour in an area slightly bigger than a county. When you see the radar, think of how many supercells there were, how many hours, how many counties with this environment. And then the tornado total that results isn't too surprising. So again, there's the sounding just to confirm what the environment looked like at just one snapshot. At Birmingham, again, most of the derived indices are off the charts. The vertical shear is very strong, the buoyancy is strong. We still have the residual lapse rates. It's very moist. There's not a whole lot wrong with this sounding by most measures. So again, that's just confirms that these model analyses were pretty good. Okay, we're going to look at this one. What were the complicating factors? At this point, we had a whole bunch of stuff that checks out. So all of these, the classic tornado outbreak ingredients, all check, no problem. What were the concerns? I've mentioned it already. It's the early convection, and what would that do to the size of the outbreak? So an event like this, you're almost certain you're going to get serious tornadoes. It's just a matter of how big is the area going to be. And at least to me, it's very important to get that area right. I mean, you could just easily carpet bomb this with it, just draw high risk from Ohio to New Orleans, and oh, well, I caught it all. There are going to be tens of millions of people that have absolutely nothing happen, that it's going to seriously question your credibility after you try something like that. So the point is, do you have good meteorological reasons to narrow the threat, but not narrow it so much that you miss the important events? Okay, I was going to try the internet connectivity and do the radar loop, but then the UCAR site crashed on me the other day, so forget that. We'll do it. I'll step through it here. We're going to talk, here's some of the things that were noticed in the morning. And again, you don't have to worry about all the details here. The idea is that there were several convective clusters or MCSs that crossed the area overnight and in the morning, and it was essentially nonstop. And the question is, where were you going to get all that mess to consolidate? And then, of course, from the west, you had a source for storm initiation. Everything favored discrete supercells, and that's what happened. And again, so the real trick was how far north is this going to go? Okay, so this is at 9Z in the morning. So we're talking about 4 a.m. Central Daylight Time. Large MCS moving across Mississippi up into Tennessee. So that's a pretty big convective system. I think people out here would get worried if you saw something like that in the morning, crossing Oklahoma and Kansas if you're expecting a big event. And it turns out this MCS had supercell structures embedded in it. It was, I believe, the most significant tornadoes between 6Z and 12Z on record. So as long as we've been keeping tornado records, this was the busiest midnight shift that has occurred. And this is leading into the forecast for April 27th. This isn't the April 27th. This is the overnight April 26th stuff. 3 hours or a couple hours later, MCS still going pretty far south into Alabama. Oh, what's that back to the west? There's storms west near Vicksburg. There's more convection back in Arkansas. I'm putting the outlook together at this point. Okay, now it's outlook time. Well, we've got another cluster. It's already into northern Mississippi. The other one to the east has weakened. So you would assume that perhaps the influence of the outflow didn't extend very far south. And if you remember back to the soundings, Birmingham was chewed up pretty good, but Jackson, just this little shallow stable layer. So the impact of the outflow didn't really go much south of I-20. And so that's why it recovered so fast. But look at northern Alabama. I mean, again, there's already another convective system that is going to cross that area before they have much chance to recover. And Tennessee to the north has little chance. But notice back to the west near the Mississippi River, you're already getting sort of scattered cellular development. And that's the beginning of the tornado outbreak is right there. Plus, there are little specks in the worm sector. This is only 17Z. By 19Z, now we've got multiple bands of supercells along the dry line, sort of pseudo-dry line trough feature in Mississippi, and other cells forming in the open worm sector. So this is normally a recipe for bad things to occur. So we're going to have multiple discrete storms in a pretty dangerous environment, and the only thing limiting this is the outflow to the north that has stabilized Tennessee. And then 21Z, 23Z, I mean, you can, even on this regional composite, you can see the appendages and some of the classic supercell structures. So again, think back to the environment we're sitting in and look at how many supercells there are. It shouldn't be any big shock that we had multiple strong and violent tornadoes, including several very long track damaging events. And there were actually several hundred fatalities. So this is about as bad as it's usually going to get. The only thing that would be different is the areal extent compared to something else. Okay, let's look at a different outbreak that had some somewhat different concerns compared to April 27th. This is March 2nd of 2012. We were in this kind of real active period, which has almost completely ceased since then. But we have another high risk. This one's focused up more toward the Ohio River, moderate risk down into the northern parts of Mississippi, Alabama. The main tornadoes were close to the Ohio River. That was the most significant activity in this event. Okay, so we're just going to look at the morning of on these next few. So instead of going through the entire evolution, we'll just look at what happens during the day. In this case, this is the evolution from 12Z to 0Z. You see a jet streak propagates out of the plains toward the Ohio Valley. Again, if you just glanced at something like that, you might say, oh no, it's not the left front quadrant, it's not sitting right over the Ohio Valley where I want it, or where my warm sector is, therefore nothing's going to happen. Well, actually in this, you can see a divergence signal over toward West Virginia, which is a reflection of the big convective system that's already going. So it doesn't, the stuff aloft is important, but it's not the primary driving factor. The vertical shear is far more important than any vertical motion aloft induced by some feature like this. 500 millibars, again, not a super high amplitude wave. The background flow is strong. The gradients are strong. I mean, if you look at this, there are winds up 90 knots at Amarillo, and notice that corridor Springfield to Wilmington, Ohio, 100 knot flow. That is pretty strong, but it's not a super high amplitude wave. It just looks like a strong ripple in a broader trough, and that's kind of what the 27th looked like. Then we'll drop down lower, 850. Cyclogenesis, a little more pronounced than the April 27th event, moves northeast from Missouri toward lower Michigan. Again, the important thing is that there's moisture hanging around to the south that's already entrained into the system, and the gradients increase. And again, a lot of this outbreak actually occurred prior to this map, so it was essentially winding down by this time. Okay, what do the soundings look like? Here's the relatively uncontaminated soundings. Shallow stable air at Springfield, Missouri, but again, relatively large buoyancy, sitting just above the surface, strong deep layer shear, long hodograph. Nashville, same kind of profile. It would be very easy in this case, you get any heating and mixing, you're gonna bring moisture down to the surface in these type profiles. So as soon as you get a little bit of sunshine, the surface dew points are gonna jump pretty quickly over a broad area when you see something like this. And then the 12Z Little Rock soundings almost uncapped to start the day. So you might suspect that this will get started relatively early. Okay, here we jump ahead 19Z, which again, this is a little earlier than the previous case. The moisture's not as rich as we see in the April 27th. Those are just 60 to 64 in the dark green, and temperatures mostly in the 70s to say low 80s in the southwest part of the area. But again, we have a relatively well-defined cyclone and a little more confined warm sector. Not as unstable as the previous one, but again, still 1,500 to 2,000 ML Cape, which is fairly respectable for well east of the Mississippi. LCL heights aren't as low as you sometimes see. These are in the 1,000 to 1,250 range. That's not unfavorable, but it's not quite in the sweet spot. And it's a little moister up toward the Ohio River, toward, say, southern Ohio. And again, that would be in the vicinity of the surface warm front. Vertical shear, broad area. Effective bulk wind difference says supercells almost everywhere. It's strongest up on the north part of the warm sector. Same kind of thing holds true with the effective SRH. Again, and in this case, you can see the warm sector mapped out pretty well by the reds, and the color fill tells you that the inflow base is no longer at the ground. So that tells you that the buoyancy is clearly becoming elevated, but it's potentially a surface base there along the Ohio River. So you combine all the factors. Again, you would expect the combination of ingredients to be maximized near the Ohio River. It's a little weaker to the south. The lullable shear was a little less than what we had to the north, and the moisture wasn't any more favorable, so the environment drops off a little bit. And again, when we go through what happened on this case, we'll leave that up for a second. We initiated discrete storms, which is what we want to see. Now, in this case, the warm sector is not as broad as what we saw before. You don't just have hundreds and hundreds of miles of undisturbed warm sector. So in this case, the storms move pretty quick, and at some point they do appear to outrun the rate of production of the warm sector, so that's going to play into how big is the outbreak area. And in this case, the moisture and the vertical shear favored the areas north. Like in the April 27th, it looked good over a huge area, and the only thing stopping it was where the instability dropped off. In this case, we need to get to the north side of the warm sector where it looks a little bit more favorable overall. So again, there's a lot of supercells to the south, but not as many significant tornadoes. So here's the radar. This is early afternoon, 1 p.m. I don't know, I guess at that point we weren't Central Daylight Time, so this would be noon. We've already got convection going in Missouri and Illinois. They already have cellular structure, mostly semi-discrete storms. This continues across down the Ohio River, and then it was during this stretch, those storms that were just ahead of this little line produced, I know there was at least one F4, I think that was Henryville, Indiana. It was one of those, it was something like that. Now notice down south, there's a whole bunch of supercells, a lot of discrete storms, a lot of these had supercell structure. There were a few weak tornadoes and a lot of big hail reports, if you remember from the severe map, but it wasn't, the main tornado event was kind of the northern part of this. Again, it was a little bit more moist, a little bit stronger lullable shear, which from the conceptual model tells us that we've got better chance for lullable stretching and stronger lullable rotation in the storms. Okay, and 23Z, and we haven't had a big mode change either. Notice there's still mostly discrete storms, some clumping together toward southern Ohio, but by and large, the storms stay discrete. Now here's one thing that comes out as a question from an event like this that is a little different than what we talked about with April 27th, and it's the case of what do you do, and I mentioned this early on, that the supercell ingredients, it's not the same problem to say how long an organized storm will go compared to will one form in the environment. So take a good look at that. That's a pretty obvious supercell. This was producing, or it was about to produce, a fairly long track EF3 tornado, and this was one of the more intense tornadoes in several decades that got into eastern Kentucky and into West Virginia. Now look at where it is on the Cape plot. And I've looked at this, and here this is actually surface-based Cape. So I've modified some profiles, and this looks like a pretty good analysis. Weak buoyancy, and the storm's on the northeast edge of it moving away. Now it's trying to destabilize in the same direction, but the point is you have to answer the question, how long will the tornado threat persist? If you have existing, well-developed supercells, they can go a lot further than you think they can in this sort of scenario. So again, there were significant tornado damage, several counties into West Virginia after this analysis. So if you get too literal about it and say, oh, well, there's not 3,000 Cape, I say that it's just gonna hit a brick wall and stop. And then, so just remember, that's the storm. You're going to be looking at that an hour later. It looks a lot like that. And you're going, why didn't it stop? And again, think of the pressure perturbations. This is an established storm. It is strongly drawing air in. It's going to do everything it can to keep going. So it's a much better, it's already got all of the features of a supercell well established. So it's going to work. It's going to do everything it can to kind of reproduce itself, even into what appears to be less favorable environment in terms of buoyancy. But remember, vertical shear was very strong. All right, finally, I'll come out to the plains. I didn't want to look too Oklacentric or any of that, but we'll get out here and look at a plains event. And this was, and we're just going in sequence, but if you hadn't figured it out, I'm just looking at them in order so that nobody would think I had any real big plan here. It's just, this is the order these events occurred. April 14th of 2012. This one, you can actually, and this is typical of the plains, you can see the supercell tracks in the tornado reports, these parallel strings of tornado reports. Usually the storms are a little more widely spaced, and this is a fairly typical event. But you do notice there's some false alarm on the south end. That was actually the outlook I put out. I went a little too far south with it down here to Oklahoma City, Norman area. And we'll talk about that a little bit. And so, the idea is how do you corral this? And notice also the storms got going a little bit further west. That's another one where you do have to think about predictability on the synoptic scale, where the boundary is actually going to be when storms form. Okay, since we've already kind of looked at this case, we'll just go through this somewhat quickly. We looked at the moisture return already, so I won't look at that part in any detail. We kind of looked at the lapse rates a little bit and some of those soundings. And we know that we have a synoptic wave. And so what are the concerns? Well, I remember from real time, people were talking about, oh, well, the wave's going to be too late. And this is an example of how you can make a successful forecast if you don't put too much emphasis on the numerical models. Because in this case, does anyone remember what the numerical model convective precip forecast looked like, even from the morning of the event? They were almost a goose egg, right? I mean, they were just tiny little specks. And people were taking that stuff very seriously. The idea that well, the model doesn't show convection. Now, we'll talk about the convective scheme some, I guess, with the numerical models. That would be like session 8. But the idea is there are questions about how the convective schemes work. So if you don't know how they work, you're going to get in an awful lot of trouble real quick trying to interpret what the model is actually forecasting. But the point is, with just a basic conceptual model of the scenario, you would, and I actually was involved in this forecast too, so I can say that what we did was we looked at it when the high risk was initiated, and this was actually a day 2 high risk, and the point was, forget the argument whether we're going to have convective precipitation based on the NAM and the GFS and these sort of the operational models. It was, we have high confidence in the moisture return, we have high confidence in the lapse rate plume, we have high confidence in the wind profiles. So we have virtually no uncertainty. We're going to have a strongly sheared, moist, unstable warm sector over a broad area. So the potential, conditional sense, the potential is very high. Are we going to get storms? Well, we're going to have a typical dry line lee trough. And then the idea is flip the question on itself. I don't care if the models don't show anything. Do you have reason to suspect that you'll get convective initiation? And that's exactly what we did. We looked at it and said, if you tell me this is what it's going to look like at 0Z on the 15th, and then you ask me to say what the radar is going to look like, if I'm going to say nothing's going to happen, I'm telling you that the radar is going to be largely blank at 0Z. I look back at the forecast soundings, I look at the background environment, and it was just, I don't believe it. I've been doing this too long, there's no way I believe that that's what it's going to look like. So when you flip the question on itself, it was like, well, there's no way I would take the bet that there'll be no storms. If there are storms, what are they going to do? In a conditional sense, the significant tornado threat was really high. So even 2 or 3 storms would be a big problem in that kind of environment. Okay, so here's the scenario. Mentioned in the comments there that would the wave be a little late? You notice it's back toward the 4 corners, so this is, Outbreak is underway at the time of this map. So the wave hasn't really merged in the plains, though the gradient has increased, but the classic trough itself is still back to the west. 500 millibars, same thing. Again, it's not the end of the world negative tilt trough that everybody for some unknown reason seems to think everything's supposed to look like, which almost nothing ever does. In this case, it's, some people might argue, oh my goodness, it's positive tilt. Oh, the world's going to end. What does it mean synoptically? In this case, it doesn't mean anything, because we'll see that there's cyclogenesis going on. Now, I don't know if you guys can read the numbers. Look towards, say, Dodge City, Texas Panhandle, and this is pretty typical of tornado events out in the central U.S. Notice the change in the 500 temperatures. Do they cool or warm? Do they? Can you read it? I'm just questioning whether your eyes work. I don't think in this case they cool. Amarillo's minus 13 at 12Z, Dodge City's minus 14. They warm. This is actually fairly typical. Cooling aloft is something that's thrown around a lot, but rarely actually happens in tornadic warm sectors. It's usually the result of what's happening down low, completely overwhelms any temperature changes aloft. But notice also Oklahoma City, what's the 500 millibar height? Oklahoma City, geopotential height, 574 at 12Z, 574. So we have the height falls, and the primary influence of the system is probably to the west of Oklahoma City, and you'll see why this is important looking at the soundings. But the gradients have increased out Dodge City and Amarillo, and so the flow's getting stronger, but we may or may not have strong large-scale ascent that has impacted the warm sector yet. 850, big chunk of moisture already sitting in Texas, strong lullable flow. We have westerlies or west-southwesterly flow over the highest terrain in the Rockies. We talked about lee cyclogenesis. That's the classic location for a lee cyclone there on the Colorado-Kansas border. 50-knot flow, high dew points in the warm sector. So again, pretty classic looking for kind of a stalled dry line case. Okay, here's the sounding. Now, so remember, everyone thinks there's not going to be any storms. All the models are so late. We'll never get any storms. So I don't even know if I should bother to chase this. 12Z Dodge City, 12Z Amarillo, 18Z Dodge City. We're not going to get any storms, and I should probably wait. And, I probably won't even have to look again until about dark or something like that. With that sounding, you're going to wait until dark. There's no convective inhibition. There's a little bit of goofiness above 850 that might be the wet sond. Point is, there's large cape, strong vertical shear, it's moist, and there's almost no convective inhibition and this is at 18Z. And it's somewhat predictable because if you look at the Amarillo sounding, that's a pretty juicy sounding for Amarillo for 12Z to be that far west and relatively early in the season. It's not hard to imagine with any heating and mixing that the inhibition erodes pretty quickly on that one. Okay, now let's look over further east where there weren't as big a height changes. This is Lamont in the morning. That typical shallow stable layer, we're way up on the north edge of the warm sector. We're probably going to get rid of that real quick. And indeed by 18Z, very deep moist layer. At this point, maybe there had been ascent going on because that kind of looks like the transition that we saw way back in the sounding examination where you see the moistening, it looks like a moist adiabatic profile and the moist layer deepens. That looks like ascent. What does this look like from 18 to 0Z? There's no large-scale ascent. So I think what's happening in the morning, we have strong warm advection on the north edge of the warm sector early in the day. We get past that, and then we're just bringing in the elevated mix layer above that from the west-southwest. So in this case, there's no evidence at Lamont that there was strong large-scale ascent going on by 0Z. We go down to Norman, 12Z, relatively uncapped, and there was some convection in northern Oklahoma overnight. 17Z Norman sounding, deepening of the moist layer, same kind of thing. 0Z, same kind of thing as Lamont. It's actually a little bit capped, but strongly unstable, tremendous wind profile. That's almost that perfect sickle hodograph where the low-level vorticity is almost purely streamwise for that storm motion. So it's a dangerous profile if you have a storm moving into that. And again, if you look at Dallas-Fort Worth in the morning, Norman ends up looking somewhat like Dallas-Fort Worth. So this was, in the case where I did this forecast, I perhaps underestimated the influence of the convective inhibition and perhaps overestimated the efficiency with which the dry line and just the vertical mixing and vertical diurnal circulations would initiate storms. So what happened is they didn't initiate terribly far south, but plenty of storms did go. So it was kind of it's a case of where you can't win them all, but the idea that there wouldn't be storms was clearly blown out of the water by 15Z that morning. I'll show you the radar. But there were limits. So, you know, you still have to be careful, and you never can let your guard down when you're trying to do this kind of forecast. Okay, here's 1Z. So we're going to jump late, and we're going to look at what it looked like in the evening when this was fully underway. There were multiple tornadic supercells ongoing, dew points in the mid-60s, classic dry line, eastern panhandle into Kansas, Lee cyclone. Cape on the order of 3,000 out along the dry line in western Oklahoma. A little bit more inhibition floating around, and you saw that reflected in the 0Z soundings further east. LCL heights are favorably low, so it's sufficiently moist, it's unstable. Vertical shear is very strong over a big area. Low-level shear, very strong. I mean, that's a little peak of 700 effective SR8. So again, anyone who thinks that it doesn't happen in the plain, oh, well, that stuff only happens in the southeast. What, southeast Harper County? I mean, you know, if that's the way you want to describe it, sure. These ingredients can be assembled almost anywhere in the right circumstances. So we have strong shear, and again, you look at the SIG-TOR parameter, off the charts. Now, the big difference in this case compared to, say, April 27th, and when you look at the radars, keep in mind what this distribution of the environment looks like compared to where the storms actually initiated. So we'll look at this stuff. We actually had early elevated storms. This notion that there'd be no storms was done by 10 in the morning, which that's pretty embarrassing if you're going for a no storm forecast, and you were off by 9 to 12 hours. That's kind of a problem as a chaser, right? I mean, I just need to get within 12 hours, right? I mean, that'll get me to see plenty of tornadoes. And again, there was eventually the typical development into Oklahoma. So let's look at the radar. This is at 15Z. So 15 to 17Z, there's already supercells in Kansas. So again, this notion, and not one numerical model showed anything that vaguely resembled this. But the observations that morning gave you a pretty good idea. 19Z, we start seeing development a little further south. Now we're getting to some of the more serious storms by 21Z. Notice they're discrete supercells the whole time. There's no real storm interactions. Maybe on the small scale there were. And then we continue 23Z, and so we just have a whole sequence of supercells, but notice development stops around 23Z. It doesn't really go any further south, and that was pretty much it. So we just didn't get any more development down toward I-40. Could be related to the wave being late, the cap being a little bit stronger to the south. Again, you have to consider this probabilistically. I can't tell you with complete certainty why storms only made it to about Roger Mills County. You know, you just have to do your best when you, and again, it's like educated guesswork doing this. Okay, final outbreak that we're going to look at before we take a little break here. This will be the 17 November. This was the last high risk that we had that was explicitly for a tornado episode. I think there was one last June, but that wasn't really a tornado forecast. That was more a wind thing. Again, up into the upper Ohio Valley. This one is a little bit more obvious trough compared to some of the previous ones. You know, some people might assign the negative tilt to this one. It's a pretty sharp jet streak, moving much quicker than some of them, so it's pretty rapidly translating. We go down to 500 millibars. Again, the wave sharpens, very strong flow. You could infer from the gradient in excess of 100 knots. We just don't have soundings in the right place on this one. And very strong gradient. So this is a very strong baroclinic wave. 850, low deepens over the Great Lakes. You just see more of a trough. This looks kind of like April 27th, where it's not a classic low moving by, but it's off to the right of the cyclone in the warm sector. But again, strong flow, and there's sufficient moisture upstream. And so let's look at the soundings. Springfield that morning. Again, this is a November case, so it's not as easy to get the elevated mix layer established over the plains, but you do see some remnants, a shallower elevated mix layer, and dew points at least in the 60s beneath that. Lincoln, Illinois, 12Z, slightly stable at the surface, but not much. And then they launched a special sounding at 16Z. Well, guess what? It's 16Z, the inhibition's weak. That's not afternoon, this is late morning. Doesn't matter. If the atmosphere is ready to go, the timing, again, like the other case, you can't get stuck on the, oh, well, it always goes at 21Z, and if I'm here by 0, you have to look at the data. In this case, we have fairly strong vertical shear, moderate buoyancy. If you get storms, then you've already got a supercell and some tornado risk. So here's the scenario at 18Z for this one. Again, a lot of these look sort of similar. There's a little bit better moisture than the March case, but remember the lapse rates aren't as steep. They're as deep a layer, so kind of canceling factors. Dew points mostly in the 60s. Moderate Cape, again, lapse rates aren't quite as steep, so it's in the 1,000 to 1,500 range. You might say, well, you know, that's not that much by Oklahoma standards, but again, this is with a strong wind profile. LCL heights predictably are pretty low over the whole area, somewhere in the 1,000 to 750 range, so that's not really a concern. Vertical shear, effective bulk wind difference, generally on the order of 70 knots over a broad area, that's very strong. Effective SRH. Now in this case, it's skewed a little south. It's not all just sitting up on the warm front. So the low-level jets out in the warm sector, big area, 500 to 600 effective SRH. So again, this is, you see the combination of ingredients and more of a mid-range sector parameter type response to this one. But again, these are fairly healthy values. You don't see, environments don't look like this every day. It's just a little bit smaller area than some of the previous ones. Okay, so let's look at what happened with the radar. This one we got late morning storms, but again, they were semi-discrete. They started off the right mode. Now this one's translating rapidly, so we're having a lot of changes going on the mesoscale, and the question is, how does convective mode and how does storm motions match up with how quickly we're developing the warm sector eastward? So in this case, it actually reduced the tornado threat later, and it transitioned to widespread damaging wind. So looking at the radar, here's 15Z. 17Z, this is pretty early. We've already got multiple storms in a broken band there right through the St. Louis area. They're already showing supercell structure. There have already actually been a couple of tornadoes by this time. We keep that semi-discrete band of storms going across Illinois into early afternoon. Now you notice up north, and look at the change in the echoes there from Illinois into Indiana. We're starting to get more line segments and looks like more cell interactions and things. There's still a few supercells in there. But then what happens is this starts to evolve into more of a squall line. So as the orientation of the system changes and storms the outflows with the convection, and the fact that it's moving so quickly, you know, compared to the other ones, that moved over 2 to 3 states just during the period of the radar loop. You didn't see that kind of translation in the other cases. So this is one where you just have to figure out when's the mode of the storm is going to when's it going to transition from something other than discrete cells, and when will the storms effectively outrun the more favorable warm sector. So in this case, remember that Kentucky, Tennessee, West Virginia case, we had a really intense supercell and pretty weak buoyancy. Well, this one, the convective mode changed. So the buoyancy by itself wasn't what killed us. I think it was primarily the change from discrete to more linear convection. And again, that's part of the forecast process. Not only, it's not just getting right how they start, it's how long is it going to remain that way. And again, we'll talk about that in the next section, ways to anticipate convective mode. Okay, so I throw this one out here, and everybody should agree it's easy to identify tornado outbreaks in some sense, but that's the hard part, is the next bullet. If you want to be credible doing this, you have to consider all the information, and it takes a lot of work and attention to detail. Again, I know this one isn't real popular in the era of social media, and I want to be the first one to spout off about the big event 84 days in advance or whatever it is, so I can claim I saw it first. The good thing is there's so much noise in the social media realm that most of your bad forecasts are just going to kind of get buried under a bunch of other dumb statements. But if you have, in my case, like I put out a forecast that's archived, it sits on a web page forever, it has my name on it. If I want to do that stuff, that's fine if I don't want to work at SPC very long, or I want to get run out because someone else will replace me. And the idea is, again, not to pose that as a threat, but it's that if you want to push yourself to be the best forecaster, just develop a solid recipe and stick to it. Don't deviate just because you want something to happen or someone else says it's going to happen that's not looking at it as carefully. And again, you have to know climatology. There are thousands of shortwave troughs that go wandering by for every handful of tornado outbreaks. So you have to know that the vast majority of the times it does not happen. And again, there are a mix of synoptic and mesoscale influences. We saw them on these last two especially, where you start getting into changes in convective mode, details in the orientation of the worm sector. All that stuff matters. And you have to consider that all fairly carefully. And again, there are concerns. We should be able to find the moisture, the lapse rates, and at least the source for initiation should be pretty obvious if you're trying to forecast a big outbreak. Well, again, when we talk about it more, there are ways to identify whether you're going to get the right mode of storms initially. You want discrete modes if you want widespread tornado events. But again, this is always kind of a delicate balancing act. If the lapse rates are too steep, that often means the EML is too warm. There's a lot of inhibition. So too much of the lapse rates can be wrong. If the moisture or the ascent are too strong, too large or too strong, you might get too many storms and change the convective mode, or essentially overturn the environment before you ever build up a lot of buoyancy. And again, you need to get discrete modes. Linear convection in an otherwise interesting environment is not going to produce the same tornado risk that the discrete storms will. And then, of course, there's a whole host of mesoscale things, and we're going to talk about that after the break. Examples of mesoscale events, and that if those factors don't line up, then everything can go wrong quite easily. So again, that's all on the tornado outbreak stuff for right now. Again, it's hard to, I know I probably didn't hit everybody's favorite event, but we could be here a week looking at every tornado outbreak that someone might want to consider. And I might be tempted to do it, but I don't have a week. So again, we'll come back we'll take a 5-minute break, and after that we'll come back and we're going to we'll downscale to the mesoscale and look at the influence of outflow boundaries. And for the plains folks, which since everybody in here probably is, these are almost all Oklahoma, Kansas, so you can be excited about that. All right, hopefully everybody's ready. I lied, that was more like 10 minutes, but good questions. And we'll go ahead and get rolling here so this doesn't go too late. Okay, we're going to jump down, kind of scale down from synoptic scale more to mesoscale. And, you know, I haven't ever seen a whole lot presented on convective outflow boundaries or nothing that's terribly organized. So I've been interested in this for a while. So I figured, since I have the opportunity, we'll go ahead and talk about that some in some detail and show several cases and some of the hazards you have to deal with in terms of how your forecast works out. Okay, convective outflow boundary. You know, what are we talking about here? We're talking about storm-generated cold pools. They're essentially small-scale fronts that are related to the convection itself. So an outflow boundary, it's just the rain-cooled air left in the wake of convection. And again, depending on how recently it was formed, how dense the air mass is, that'll give you some idea how this is going to behave. And then keep in mind, these are usually not driven by the large scale. It's a mesoscale phenomenon. And there can be responses, like in the case of April 27th, where the large scale response overwhelms the remnant outflow, except where storms keep going and reinforcing it. So in central Alabama, the outflow washes out, the warm sector is reestablished. But again, the important thing here is that when you start getting on the margins of events, usually I'd argue that most serious big-time tornado outbreaks don't require a whole lot of these small-scale features. There have been people over the years that have tried to make cases for, you know, every tornadic storm is interacting with a boundary, and I'm sorry, I just have not seen the evidence. It's not been very clear to me, so I think that in rare cases, the background environment provides sufficient buoyancy, moisture, vertical shear for tornadic storms. However, there's a lot of cases, the more typical warm season cases, you need some sort of augmentation. And again, if you take that last little bullet, the important thing with a lot of these outflow boundaries is what they may do compared to the warm sector is reduce vertical mixing, which says something about how the moisture is distributed in the vertical. And that also says something about the vertical shear, because you go back to session 1 in a perfectly mixed boundary layer, deep mixed layer, you redistribute momentum as well as temperature and moisture. So vertical shear is never going to be particularly strong, or it shouldn't be in a well-mixed boundary layer, because you're constantly redistributing momentum. So it's going to end up with sort of the same kind of winds, moisture, and temperature through the same layer. So having reduced vertical mixing actually can set up a thermodynamic profile that favors stronger vertical shear in the low levels. Okay, so here's an outflow boundary case. I think this one is, I want to say it was September 1st. I don't remember the date. I think that's what this one is. It was this past fall, early fall. Okay, so this is, I've marked the boundaries using our fancy operational software. So the outflow is looks like the dash dot line there going from northern Oklahoma into Arkansas. And we'll just step through, and you can see during the day, so we have the convection that caused the outflow is moving off into Missouri and Arkansas. And if anyone notices the little ripples in the cloud structure, those are probable gravity waves. That are little disturbances moving through a stable layer at the top of the moist boundary layer. So essentially it's the cap boundary layer, and that little stable layer keeps the waves intact. And so you'll see them ripple out from the disturbance, which was the convection over in Missouri and Arkansas. And during the afternoon, notice the sun's out to the north of the boundary. We've actually got a cloud line that defines it pretty well, and it seems to be creeping north toward Kansas. And you see some evidence of cloud streets, the little fish rib things. They're not billow clouds, but they're more cloud streets in the warm sector, perhaps. And then the same thing, it breaks down to a more convective structure in the afternoon. You see moderate cumulus and lots of little bands that go up and intersect with the outflow. And we maintain a low, and then what happens in the evening, we get storm initiation essentially in several locations along the boundary. So this is a case where you saw sort of the classic evolution where the convection goes by in the morning, it gets well removed from the area where the storms later formed, it has plenty of time to modify, but it maintains its identity and serves as a focus for initiation later in the event. So let's look at this one from an environment radar perspective. Now I'm highlighting here just the site of the Lahoma sounding, because that's one of the pieces of information we'll have to verify these analyses with. But you see the storm, that one that's just to the northeast of my star, that was, I believe, the start of a tornadic supercell that was right on the outflow. Notice it's on the northeast edge of the Cape. Those max values are somewhere 3,500 to 4,000 that it's sitting right on the northeast edge of. Vertical shear in the broad sense, it's kind of on the south edge of the westerlies. This is common with the tornadic outflow boundary cases where you just don't have strong vertical shear everywhere. It tends to be enhanced along and north of the boundary. And in this case, you can tell the stronger synoptic flow is up toward Nebraska. So this is just on the southern fringe, and it's the slightly back flow in the low levels is what helps enhance the deep layer shear. So if, again, we look at, and that was looking through a real deep layer. We were looking at 0 to 8 kilometers there. This is the effective bulk wind difference. Sort of marginal supercell values in northern Oklahoma, but solid supercell profile in the southern Kansas, and that's where the storms are initiating. Effective SRH, there's a max just northeast of the storms. That's 300 to 400, so there's clearly some enhancement to the low-level shear compared to the warm sector to the south, where SRH values are closer to 1 to 200. And then the LCL heights. Now this is typical of a later season case. Notice the LCL heights are relatively high. They get above 1250 or closer to 1500 out in most of the warm sector, but much lower LCL heights in that cooler, moister environment along the outflow boundary itself, but there's still strong instability there. And when you combine it all, here's the SIGTOR parameter, pretty strong signal, southern Kansas. And again, those storms are kind of riding in the gradients. It's common for storms to be on the gradients in a lot of these cases. So let's look at the sounding. Here's what we had as a sounding from Lamont. So this kind of confirms what it looked like just removed from the outflow boundary. This is actually the warm sector sounding just south of the boundary. Vertical shears kind of on the margins for what you'd expect for supercells. Low-level shears, nothing particularly special. And you notice that the temperature dew point spreads are relatively large. So the boundary there's a little bit on the dry side, and that would convert to a high LCL. Gosh, I'd have to read this one. It's 1800 and 1857 or whatever. That's way on the high side for a high-end tornado threat. So that's kind of a dry boundary there, which again relates to potentially some problems with the thermodynamic structure of the rear flank downdraft, all else being equal. All right, and another factor you have to consider, again, we're kind of on the southern fringe of the flow, but this is 500 millibar heights in vorticity, and you see the convection there along the Kansas-Oklahoma border, it's not terribly far removed from a little speed max that's moving across northern Kansas and southern Nebraska. So there's potentially some influence if the system slopes down to the southeast with height, which it did if I didn't show all the upper air maps, but the influence down to 700 millibars gets into southern Kansas. So there's a weak background synoptic, potentially weak forcing for ascent, but it's weak. At least it's not strongly subsident. And we have a sharp low-level boundary, and the boundary itself enhances the low-level moisture and the low-level shear and the deep layer shear and provides a source for initiation. So essentially the boundary ends up being the critical factor for tornado production. And here's just a couple of the pictures, just the tornadoes. These were, I don't remember what they were rated. I don't know if these were significant. I imagine looking at the foreground there, they didn't hit a whole lot, and I don't think they did. But potentially at least somewhat significant tornadoes. So, and again, it wasn't like there were tornadoes everywhere. In this case, I think, most of the chasers, obviously these guys recognized where they probably need to be hanging out. And they had to be patient because this was pretty late. It was towards sunset. You can tell from the pictures. So, as long as the boundary's hanging around, you may have to be patient with these things. Okay, I'm going to show another tornadic case. And this one, again, it's similar to the first one. This is sort of what I see as the prototypical case. And you get the boundary pretty well defined. There's no question about moisture, buoyancy, and all that. And the vertical shear is clearly enhanced on the cool side. And you initiate storms in the right time and place, and they interact with that environment and produce several tornadoes. There were more than those. So this is the May 24th of 08 in north central Oklahoma, just to the north of here. And if we look at this, so we got, again, convection, looks a lot like the last one. It's moving across Missouri and northern Arkansas. And if you watch, you can see the change in the clouds there down toward I-40 in eastern Oklahoma. That's the outflow boundary. And you'll see in the surface obs, this goes back to the northwest and intersects the north-south dry line somewhere in north central Oklahoma. And that's where storms, so now at this point, by 1815, you can kind of trace it out in the cumulus field. You go from about Fort Smith, Arkansas, west-northwest up toward Enid, and that's where the boundary intersection occurs, and that's where storm initiation occurs. Now notice this is 1815Z. This is late May. This is pretty early in the day. If you're not paying attention to the scenario, or in the case of some unfortunate folks, we're focused on Nebraska for this day, which is a very bad move in retrospect if you want to see tornadoes. You might just look right past this stuff because, again, the stronger wave was up to the north, but again, there's a lot of mesoscale factors that favor this. So storms keep going, and then by 1915, that new storm to the south, that ends up being the tornado producer. Blows up, and we keep a slow-moving cluster right there at the boundary intersection. So what does the scenario look like? Here's 15Z. I've sketched in roughly where the outflow boundary is. Again, dew points upper 60s to the low 70s south of it. There's a dry line and a bit of a weak low. The gradient is maintained through the end of the afternoon along the boundary, and it just kind of creeps north just a little bit. So you see the moisture is surging northward. It's warming up to the south. You can imagine it's Oklahoma, it's May, there's going to be a pretty big cape as temperatures get well into the 80s with dew points in the 70s. And indeed, that was what was occurring. And then the stars where the storms were forming and moving into. And this is what it looks like at 18Z. So we've already got pretty strong buoyancy. We're on the north side of that. Vertical shear through a real deep layer, 8 kilometers. It's kind of on the southern margin of the supercell environment. Effective bulk shear puts us into the supercell range. And again, you need to be north of the boundary. You notice the shear drops off pretty dramatically south of it. Low-level shear is enhanced on the cool side of the boundary, but the key here is the cool side is not that cool. It is moist, but when you wrap everything together, there's a collocation of the strongest ingredients, and they focus right on the cool side of the outflow. And then just to show that it stays like that through the afternoon, so 18Z, it's obvious, 21Z, the same signal's there, and it continues. So what happens is we had storms forming and moving into that, and most of this tornado episode was over by 22Z, so by peak tornado climatology for late May, this one was actually almost done. So again, have to look at the environment, and consider everything. The climatology is helpful, but it should not be your primary reference point on any forecast. Okay, now here's the problem. These tornadic boundary cases, I have one from September of 2014, and then I have one from May of 2008. How many years between those two? Lots. Good six and a half years in there. It's not easy to find them. Most boundary interactions are not particularly helpful, or something else goes wrong. So the problem is, what is storms trying to do? When we talked very early about this, the storm is trying to bring potentially cold, dry air to the surface, process warm, moist air up and out. It's trying to stabilize the profile. And that's what most outflow is doing. So when you get new outflow, it acts like a strong mesoscale cold front. It tends to surge out, and any storms that form end up on the cool side of the boundary, and the air is cold and stable near the ground. And you can't support low-level updraft stretching or low-level rotation in that cold, stable air mass. And oftentimes, there may be a big increase in shear, but there's no cape with it. So again, the outflow is doing what it should be doing. And of course, they have to form in the right time and location to take advantage of the mesoscale environment, or it doesn't matter. Okay, so let's look at another case. Here's one. Outflow boundary sketched in. We're focusing, again, that's the Lahoma sounding site. Those are low 70 dew points, and I guess temperatures in the mid to upper 80s. So 80s over low 70s, pretty juicy boundary there. Moderate buoyancy, again, close to 3,000 ml cape, kind of strung out along the boundary. Now the deep layer shear, as we've seen in the other cases, it tends to be skewed a little bit toward the cool side. Extends maybe a little further south in this case. Effective bulk shear, same thing. Right there in the vicinity of the boundary, but it looks like a supercell profile on the cool side of this outflow. And again, a max in the low-level SR8s. That's pretty large values, 300 to 400. So as you would expect, this is going to not look too bad as long as it's moist enough, and indeed, LCL heights are at least modestly low, not too far above 1,000 meters. So when we combine it, we've got another little max. Now notice the magnitude. The combination of ingredients looks pretty similar to the last case, right? Same magnitude, it's over a few county area. There's a nice belt on the cool side of the outflow. And then we go to 0Z. So the buoyancy has now shifted north, the boundary's retreated. Now we've got 4,000 cape is the peak. SIGTOR parameters actually come up even larger, so now we've got an even more interesting combination of ingredients. And then here's, that I didn't show in the last one, this is low-level convergence and vorticity. So the convergence is in the red contours. So the question here is, how convergent is it on this outflow boundary? Do we have a source for ascent? Are we sure we're going to initiate storms? You can look and see up in Kansas a belt of convergence and vorticity, which is on the more synoptic cold front, which is farther to the northwest, and then there's a bit of a surface low out towards Slap Out or wherever in the eastern panhandle of Oklahoma. But it's only weakly convergent. So we've got a pretty volatile environment, weakly convergent. Okay, and this one you can see the outflow boundary pretty well. I mean, really well right there. You see it arcs back northwest from east central Oklahoma up into northwest Oklahoma. We get convection. We've got towering cumulus going up. This is 21Z, so it's 4 o'clock in the afternoon, and we've got, now this is a summer case, but we've got towering Q going up at the intersection of the boundaries. We've got what looks like a tornado environment downstream. Question is, what's going to happen? Oh, we've got storm initiation. We try to initiate another storm. It floats off, and that's the end of it. So we never actually developed a sustained supercell. So the question here is, you can have all the parameters you want, but you actually have to have deep moist convection that's sustained. There's the sounding from Lamont. This is a proximity sounding. And keep in mind, this is August in Oklahoma. So this, and anyone who remembers back to the very first slides I showed was the Lahoma event, which was August in Oklahoma. So I've kind of a little gun shy about late summer. Most people say nothing happens, and in this case, nothing did, but pretty interesting profile. Modestly strong deep layer shear, very strong low level shear. It's moist, strongly instability. It's well into the parameter space for significant tornadoes. I mean, well into it. All that happened were a couple of hail reports, mostly way after dark. And in this case, that's what I put out as a watch. So again, I'm not going to say that I'm perfect and that I'm going to get these things right every time. So you can see the problem here is there's a cost-benefit analysis you have to go through. I figured the cost of not covering this with a watch, if a storm or two gets going, I was going to look like a fool, given the environment. And again, let's just go back and think about the sounding for just a minute. Again, we launch a supercell into this kind of profile. I don't think anyone would be terribly surprised if there was some severe weather and perhaps even a couple of tornadoes. But we didn't sustain storms. And I remember struggling with that. Are we going to get storms? And at some point it becomes a yes-no decision. You have to decide to do it or not. And I guessed wrong. So in this case, it didn't work out so well. So it just goes to show that it's tough and you're not going to be perfect no matter what you try in this business. Okay, we'll look at another outflow case. This is one where you see it again. These things seem to be pretty common. Southern Central Plains is the most common area for these episodes to occur. Got the outflow. Convection in this case has moved further south down toward northeast Texas. It's pushed the outflow back west through Norman, but it's kind of sitting there in northwest Oklahoma, and you have towering cumulus forming on the boundary. Again, just keep in mind the temperature, wind fields. The dew points are in the 68 to 72 range on the cool side, those lime green and yellow dew point observations. It's pretty warm south of it. You have some deeper towers forming on the boundary. And then, so that's up through about 23Z. So the question here is, what does the environment look like? So this is, again, we're going to highlight Lamont since we at least have a sounding from there and we can verify. Here's the convergence field, 23Z. Here's the buoyancy, so pretty large cape again, 3,000 to 4,000 up in the northwest Oklahoma. Now in this case, the vertical shear through the real deep layer is not quite as strong. So this is has more of a warm season look to it. The effective bulk wind difference, you're kind of on the margins for supercells. LCL, you see a bit of enhancement on the cool side of the outflow, and again, reflected in the SIGTOR parameter. Not as big as the other cases. It's not quite as favorable an environment. Here's the sounding from Lamont. In this case, you notice the winds aloft are a lot weaker. Notice that the 15 knots there, 500 millibars. So we have an outflow boundary, and we saw towers developing. So you might say, oh, well, this is slam dunk. I expect to get tornadoes or whatever. Well, let's look at the large scale. And again, here's where we were focusing. There's not a whole lot going on. 500 heights of vorticity, there's little that you could track through this. There's no substantial wave that you can point to, so there's really no large-scale component to this scenario. And because the background flow is relatively weak, it's kind of on, the outflow itself is only able to get us to the lower margins of supercell parameter space. And what happened? Nothing. So you didn't get storms at all. These are common problems. And because you can't ignore the convective initiation part. Conditional risk means nothing if you don't meet any of the conditions. And in this case, without a sustained supercell, none of those supercell tornado ingredients mean a thing. All right, so here's a new outflow case where it was just generated by the convection relatively recently. It's moving south, but it's starting to slow down. But it's relatively cool in the outflow air mass, and unfortunately, we didn't have any local observations to see what the wind profile looked like on the immediate cool side. And it's not always in Oklahoma. So here's, for one of our guests here, we've got an Arizona case. So this is one where this is from, again, this past late or early fall, late summer, we had an outflow in central Arizona off the rim. So this is out by Phoenix. Same physics hold in Arizona as here. Notice the dew points are in the 60s in the warm sector with the greens down there and temperatures in the 80s. We have storms, and what we're going to do is focus on the storm down there where the trough dry line out, or essentially a pseudo dry line and the outflow boundary intersection occurs, and see what happens with that storm. And that's this one. So it's got a supercell shape to it, and indeed this was a supercell storm. This thing moves off to the northeast. This is probably peak intensity. It's got a nice appendage, sort of a typical supercell structure. But then what happens to it? So the key is you have to think about where's this storm going relative to the outflow. Let's look at the storm relative velocity. Yes, storms can rotate in Arizona. So this is a nice tight little velocity couplet. And this is what typically happens when you see these storms. But notice it weakens pretty quickly. So we have this pretty rapid little spin up, and then it weakens as it moves off to the northeast. So this is pretty typical of what you see when storms, pre-existing storms, encounter relatively cold new outflow. Right on the edge of the outflow, there's an enhancement in the shear profile. You end up with stronger horizontal vorticity due to the thermal gradients. You get stronger tilting and stretching, a stronger low-level mesocyclone, stronger pressure perturbations down close, stronger stretching. Everything kind of feeds back on itself pretty rapidly. However, as soon as the storm moves very far northeast, it encounters what's happening down near the ground. It's stable. It doesn't matter what the wind profile looks like. That air can't feed the updraft, so the idea of like the effective inflow layer starts to recede well above the surface. So if we look at what happens to the deep echo top, I don't know if people look at this terribly often. This is near peak. You see these higher echo tops that are 45, 48,000 feet on the storm top, and the echo top just collapses down to 30. So basically the entire updraft weakens as it moves over the cool air mass. And so the question is what happened? Now in this case, I don't think anybody was out there. I have no idea if a brief tornado occurred. There wasn't anything reported. But it's interesting nonetheless. And again, just to reinforce, this can occur in Arizona. Occasionally you see it even in parts of the interior Northwest in the summer. And of course all over the central U.S. and eastern U.S. Occasionally you'll find these events. But by and large, Kansas, Oklahoma, and Texas are the most common areas for these outflow cases. So again, if you're looking at the outflow and you want to see tornadoes with these events, you want the strong surface heating on the cool side, because I could have shown thousands of terrible cases where the outflow is just racing off to the east or southeast and tearing everything up. You don't want to see it moving very fast because you want to keep storms in that zone where the shear and the moisture are enhanced the most. You know, the further you go into the cool air, the more of a battle you're doing with weaker buoyancy. And again, you need to have, a lot of times these are the difference between supercell and not. You know, if you just get too hung up on the background environment, the idea here is you have to look at, if the background pattern favors supercells or tornado, you don't need all this stuff, and a lot of times you won't even see it. But if it doesn't, then you have to start looking at these things. And a lot of these surprise chase events are cases where, you know, your buddy was looking at this stuff, you decided to sleep till 2 in the afternoon or whatever it was, and you woke up just in time to see, hey, that's a kind of a neat looking storm, and why am I sitting here? And, you know, and I think of events, you know, you might not be paying attention, maybe it's Bennington or something like that from, no? Ben's shaking his head up there. Yeah, apparently I hit a soft spot with I was working, so I didn't see it either. And again, you also have to get storms. So I showed that I've fallen for this myself, where we didn't get initiation and things didn't work out. So it's the same kind of idea. You need moisture, instability, vertical shear, lift, discrete storms. It's the same recipe, just on a smaller scale. It's different factors putting the ingredients together. Okay, so that wraps it up for tonight, and thankfully I didn't go too long. And what we'll do next time, which will be 2 weeks from tonight, we will resume looking at convective mode, and we'll talk about how do we forecast discrete cells largely in these synoptic events. How do we tell the difference between a squall line and a string of supercells? So we'll look at that coming up here in 2 weeks, and thanks for coming, and enjoy your spring break.